Hello, this is Dr. Christy Patton-Lukes, and in this lesson we'll be looking at heats of reaction and introducing Hess's Law. So we've been doing balances on processes, but in this chapter we'll add reactions into the process. Now, our simplified energy balance, if I neglect the potential and kinetic energy, for a steady state system would be the mass times the change in enthalpy is equal to the heat transfer plus the work. And for a closed system, the mass times the change in internal energy is Q plus W. The delta here is going to indicate the total change from the beginning or the inlet to the end or the exit. And in the last chapter, we learned how we could include changes in temperatures, changes in pressure, and change in phase. What we're going to be adding in this chapter is including chemical changes via reaction. Now those reactions, you probably learned this in a chemistry class, but just a reminder, those reactions can either give off heat or energy, in which case they're exothermic, or take in heat, in which case we call them endothermic. These energy changes are going to be part of that delta H or delta U that we need to calculate. So we want to learn how to quantify that. So let's look at heats of reaction. Heat of reaction is going to, in general, be a function of temperature and pressure, and it's going to be the difference between the enthalpies of the products minus the reactants. Now, the little circumflex on the top of the H indicates it's typically going to be on a per mole basis. That's going to be per mole of reaction. So you need to have the reaction written out in a particular way, and this is going to be tied to that. We'll look at this more closely in an example soon. But those H's are going to be multiplied by the stoichiometric coefficient from that reaction. So therefore we write them as H of the products, not specific H of those products and reactants. Now all of these reactants and products are going to be at a designated temperature and pressure, and the heat of reaction changes with that temperature and pressure. Typically, data is only going to be available at 25 degrees C in 1 atmosphere. So in that case, we are going to designate that the standard heat of reaction. And so instead of having to put parenthesis 25 degrees C, 1 atmosphere, we're just going to put a little superscript 0 on the delta HR. And this will indicate it's the standard value, and we just know that that means 25 C and 1 atmosphere. Now the trick is, just like we've done before, we can take our process through any hypothetical path. So the easy thing is, bring all of those reactants and products to 25 degrees C, 1 atmosphere, have the reaction happen there, and then it's not a problem that that's the only heat of reaction data that I might have. Now, just a few facts about heats of reaction. First of all, delta H of R is going to be negative when the reaction is exothermic. If it's positive, it means it's endothermic. When the pressure is low or moderate, meaning near atmospheric pressure, delta H for reactions will vary with temperature, but not significantly with pressure. So typically we can neglect pressure changes. Also, the value of delta HR depends on how the reaction is written. It's based on what is 1 mole in the reaction. Also is going to depend on the phase. So it might be solid, it might be gas, it might be aqueous, it has to be dissolved in water. For each of the species, that's going to make a difference. And finally, I can relate enthalpy and internal energy change for reactions using this expression here. Only the gases make a difference in U and H. And so I'm going to subtract off the PV for each of my gaseous reactants and products. But if I assume they're essentially ideal gases, then the easiest thing to do is take delta H of reaction minus RT times the difference in stoichiometric coefficients of products minus reactants. And if you want to play with that a little while or read carefully in the book, you'll see that that's derived from assuming that the gas phase is essentially an ideal gas. So how do we measure or calculate heat of reaction? Well, one thing that's easy to do is to look at known reactions and their enthalpy changes and use those to compute for other reactions that we may be interested in. So for instance, if I have reaction A plus B goes to C with heat of reaction 1, and B plus C makes D plus E with heat of reaction 2, can I use that to predict A plus 2B going to D plus E? I can look at this and see that there's a lot of similarities between these two reactions. So this brings up Hess's law. Hess's law says that if the stoichiometric equation for reaction A can be obtained by algebraically combining reactions B, C, whatever, then the heat of reaction for A can be found by performing whatever algebraic operations on those heats of reaction. So in this particular case, I could get reaction 3 by adding reactions 1 and 2. Therefore, I can add the heat of reactions 1 and heat of reaction 2 to get the heat of reaction for that third and final reaction. So let's look at an example. So I have reaction 1, carbon plus oxygen makes CO2, and the heat of reaction here is quantity A. And I have another reaction, carbon monoxide and half an oxygen combined to make CO2, and that has heat of reaction B. So what I want to do is figure out what's the heat of reaction for carbon plus half an oxygen to make carbon monoxide. In this case, I'm going to subtract reaction 1 minus reaction 2. So if I do that, I have C plus O2 minus CO minus 1/2 O2 goes to make CO2 minus CO2. If you simplify these, I have an O2 minus 1/2 an O2, so I have on the left-hand side carbon plus half an oxygen minus CO makes 0. And that's a 0, the quantity, not the oxygen atom. So the one with the negative coefficient, let's move it to the other side. So therefore I have carbon plus half an oxygen makes CO. Well, that's the heat, the energy or the reaction I'm looking for. So therefore I can use these same steps to calculate the heat of reaction. So I had taken reaction 1 minus reaction 2. The heat of reaction, therefore, is A minus B.